Recording is on.
So I think it's working.
Yeah.
Let's see how much space I got because it records to Dropbox. Let's see how much space I got.
Oh, and on Mac records to Dropbox?
Yeah, that's the only option. When you record it to Dropbox.
Okay. 1 minute. 1 minute, and I'm going to get started. I don't know where Eric. I needed to talk.
No, Eric's not going to be here. He's out in BC.
Oh, that's right too. That's right.
So you might as well get started, Eric.
Yeah. Okay, may as well. Welcome everybody, and we have a new visitor here, Mike. Want to introduce yourself?
Well, as most people know, I'm Mike V3MKX. I'm up here in Aurelia. I used to be out by Perth and out back in Barrie. I've been in the hobby, oh my goodness, over 30 years. I grew up with ham radio. My dad's a ham, and it's in my blood. I enjoy building stuff. I enjoy CW sideband. Pretty much any facet of ham radio interests me. Go down to the Dayton 4 Days in May QRP event, which is a blast. And that's it. I could go on for hours, but I don't want to bore you. It's, the usual stuff.
That's right. Well, welcome to our meetings.
Thank you.
I just wanted, there's nobody else new. That's it. Okay. So last night I was at the PARC executive meeting, and John always puts on the agenda buildathon. So I told him it's not buildathon, it's the HB group. The buildathon happens to be part of the HB group. So please change it to the HB group. So I've been keeping them up to date as to what's going on with that. I also mentioned to them that we are recording our meetings, and they're going to be put up onto YouTube. And John asked if we could put a YouTube link on the website. And I told him, I personally don't, it doesn't matter to me. And then Peter pointed out, we put all our HB stuff up on the website. So I told the guys when it's ready to go, then Peter can send Peter Taylor a link and he can post it. And that's that. So tonight we've got Dave. He's going to talk about FFT and LT Spice. Take it away, Dave.
There, can you guys see my screen?
Yep.
Okay, and you can hear me clear, right?
Yep.
Perfect. Okay, so this is I don't know what is this? 1, 2, 3. This is the fourth presentation in a series of 5, and it's about me going down a rabbit hole. And as always, let me start off by saying I'm not an expert in this. This is just what I kind of found out going along the way, and it could be right, it could be wrong, but just don't hold me to it. And it all started from me looking at a buck converter and not being able to make it work in LT Spice. And then I started looking at LT Spice to why this stupid buck converter couldn't work. And it led me down a whole bunch of rabbit holes where we talked about inductors, MOSFETs. And finally, by me talking about MOSFETs, I started looking at a build, a transceiver Peter and I were working on. I called the Dueling 612, the D612, and the power amp there wasn't working very good, so I started to take a look at that. So that's what the conclusion of this presentation is about power amps. So today we're going to talk about FFTs, how to do an FFT in LT Spice, and let me get down. Where am I here? I know I could put this into presentation mode, but I find this easier, especially since I gotta, sometimes I'll be jumping around from slide to slide. This way I could see my thumbnails. And I think it's big enough everyone can see it. So this presentation is about FFTs and LT Spice, but more, there's a little bit of background about FFTs. And by the end of this, your brain is going to hurt. So just again about the buck converter. I looked at the buck converter. I couldn't get it to work. Here was a design I ran across. I couldn't get it to work, and I went down the rabbit hole of trying to understand how a inductor works and why doesn't a MOSFET work, and what that eventually led me to was this thing called a high side bootstrap circuit, and that's necessary to turn on a MOSFET in a high side switch, which is what we've got here. And once I figured that out, the current and voltage came out exactly what was predicted here. So everyone was happy. But, you know, to get that to happen, I had to look at MOSFETs and how they work and why, you know, the MOSFET wasn't working properly. And that rabbit hole led me to understand that there's a lot of capacitance involved in these MOSFETs. And I create a little model of a MOSFET here based on the capacitances just to measure the input impedance. So here's an LT Spice model for IRF 510. I created this based on parameters here for the IRF 510, and they match exactly. And as you can see at high frequencies, these MOSFETs basically short out. So with that in mind, I started looking at my Dueling 612 because I thought, okay, well, maybe that MOSFET I've got is horrible. Maybe I should get another MOSFET. So in the last presentation, I started looking at other amplifiers and looking at other MOSFETs. And there was a mistake made in that presentation and had to do with the use of log versus log 10. And I found out that in LT Spice, log refers to the natural logarithm. It's a log E, log base E. So it's based on e to the x, and you need to use log 10. So in my measurements, I used the natural logarithm, and so all my measurements were off by a factor of 2.3. It's a math thing. Just don't question it. It's off by 2.3. And so in the last episode, in the last presentation I did, you know, I talked about my Dueling 612 power amp, and I took a look at that. And one of the problems was it wasn't legal. So, you know, according to Canadian regulations, for a 5-watt emission, like you have to be about 43.5, 10 watts is 44. DBC, I call it DBC, it's dB carrier. That's the emission from the carrier. It's actually fundamental. So whenever I say DBC, I mean fundamental. I don't mean carrier. Carrier's applicable for like a CW, where you're putting out a carrier. But in sideband, where the carrier is suppressed, there is no such thing as a carrier. It's the fundamental frequency. So my bad, I'm going to use DBC, and I don't care what anyone says. It's just I'm using that. So it's got to be 44 dB below the fundamental, and I was getting about 40 dB, and which meant the D612, the amp was garbage. It wasn't good. So there's a bug in it. And so here's the measurements I made of the various amps. Here was the original 612. By the way, all these measurements are in LT Spice. Everything I do here is in LT Spice. There are no measurements whatsoever outside of LT Spice. And so that was my original power amp. It had about an 8 dB roll off. And here's the other power amps I took a look at. And these, I fixed the log 10 issue. And also, too, what was missing was conduction angle. That was missing out of the measurements here, so I had to adjust that. And so these are the accurate roll-offs there. But I'll explain that more in my next presentation when we start looking at measurements. I'll talk about conduction angles. So what I decided to do was to take each of those power amps and I would swap in various MOSFETs, and I would look at what the performance was in LT Spice. And basically what I said I would measure was, these parameters here, just to see how well it was performing. And basically there was only 3 things I had to measure. I had said at the time I had to measure, which was the purity, to ensure the spectral purity, to ensure Industry Canada compliance, the output power, and how much power is being dissipated by the MOSFET. But what I needed to also measure, and there's a bug in me saying this, I had to also measure conduction angle. So when I get into my presentation on measurements, I'll talk about that. So today, what I want to do, that was just a sort of a background of where we were or how we got here. So this evening, what I want to do is I want to give a little bit of background about the Fourier Transform, talk about a little bit about what a continuous transform, discrete, and fast Fourier transform is, then talk about some important parameters for FFT, which becomes very important when you look at doing an LT Spice FFT or even doing an FFT in your scope. Now, in the case of a spectrum analyzer, that's all done for you in the background, and you could just turn this off. If you're just using a spectrum analyzer, all this stuff is done for you in the background, and you never need to know anything here about a discrete and continuous. But I'll advise you right now, some of your brains are going to hurt by the end of this conversation. And you may not get it depending on your understanding of math and integrals and summations and that kind of stuff. But that's okay. You don't need to get the math. I'm going to try and explain it without using math, and hopefully you gain a high level understanding. So what's the Fourier transform? So let's start with the Fourier expansion. So this dude way back when, by the name of Fourier, don't ask me what his first name is, he came up with this and he said, okay, any continuous function, and a continuous function is like a equation. So it's a blackboard equation. You're going to write the equation out on the blackboard, and you've got an equation which describes one of these things. So you've got some equation called f of t. It's just an equation, okay? He said that continuous function, that equation, that function, can be broken down into these terms: a sum of cosine terms and a sum of sine terms. And each term has a coefficient in front. So here you see the A1 term applies to just t, f of t, the same t. Here's 2t, the a sub 2, which is the coefficient for that term. So you can think of these cosine and sine terms at different frequencies. They're kind of like different frequencies. And you could think of these coefficients as volume control knobs. So if you think of those mixers, you see that, in a recording studio, they got all those knobs, they tweak. So that's what you're doing here, is that you're tweaking all these coefficients and saying this term has more content than this term, and you're just tweaking it. So that's the Fourier expansion. So with a little bit of math, that's how you write the Fourier expansion. Okay, and so you can arrive at these Fourier coefficients. These are these coefficients here. You can solve that equation, and you can get these terms here. And so, for example, for a square wave, let's look at a square wave. So we've got a 3-volt square wave here. It's got a DC offset. Remember Michael's conversation last week where we talked about a DC offset? So in this case, the DC offset is 1.5 volts. There's a DC offset of 1.5 volts to bring this up, right? So if we look at this, these coefficients here, what we'll find is that the cosine terms disappear. The cosine terms integrate to 0. It's a math thing. Don't worry about it. Just the A terms are 0, and only the B terms are valid. So if you look at this, your terms works out like this. So the DC term, which is this first term here, this first term is your DC component. There's no sinusoidal component to that. That's just a fixed number. So that's called your DC term. So in this case, it's your A naught, the amplitude divided by 2. If you work this out for for A sub 0, well, here's A0. You do this math, and it comes out to the amplitude by 2. So the amplitude's 3, divide by 2, 1.5, and lo and behold, it works. And so for the terms, for the even terms, if you solve this, they become 0, and only the odd terms comes out. And it's 2 times the amplitude divided by n. And remember, way back when, there's a comment Hassan made way back when saying, oh, the coefficients drop as a function of 1 over n. So that there's the proof of that. So for a 3 volt peak-to-peak sine wave, here's the volume knobs for the B terms. B0, 1.5, B1, 1.9, B3 is 0.63, B5, 0.38, etc. So if you take these terms, plug it into that Fourier expansion, right, you get a square wave coming out. Right, so now, if you look at this, we are multiplying the function by a sine, or the function by a cosine. We're doing a multiplication here, and we're doing this fancy thing called the integral. So basically what that's doing, that's a correlation. It's called a correlation. You're looking to see if this sine term has a high correlation of being into that function. Is this function part of it? Are they correlated together? A high correlation means that a lot of this function is in that function. So here's an example. So here's the f at x term, and here's the sine x term. So in this case, the f at x term is exactly the same as the sine x term, so the correlation here is high. There's a high correlation because sine x is in fact part of that fx. So now if this is the sine x term here we got 2 bumps, 3 bumps, and we got 1 bump and, a bump and a bit. You look at this, well, there's not much of this. The correlation here is low, right? And in this case, here's the same signal, f at x, same signal, and here's this term here. And so in this case, the correlation is also low. There's not much of this in there. So basically all you're doing here is a correlation. Now, the reason that you've got sines and cosines here, this is important, is that because if you look at a sine wave and you look at a cosine wave, the sine wave starts at 0 and the cosine starts at 1, right? If you're looking at it on a unit circle, you're just looking at a value of 1, right? There's no large amplitude. There's a phase shift. So you could say the sine is a 90-degree phase shift from the cosine, or vice versa. So if you take these 2 waves and you combine them, okay, you'll see the resultant wave. There's a phase shift here compared to this function from this waveform here. It's shifted. So it's as if this waveform is shifted this way. It's shifted to the left. And this waveform here is at the top. You could see it's as if this has been shifted this way. So by using sine and cosines, you could get the phase out of this as well too. Coming out of the math, you can get the phase of your signal. Okay, so the Fourier transform basically is are these coefficients. So, and they're telling you how much of a specific frequency is involved. So it's telling you, for example, how much of 1 megahertz is in that signal, or how much of 13 megahertz is in your signal that you're measuring. So in this case, here we've got 1 frequency, single waveform. So we've got 1 coefficient. Theoretically, we've got 1 coefficient, it's a pure wave. There's 1 value here. And this is in the frequency domain. So this we're plotting the intensity and versus frequency. So n turns out to be your frequency, right? So this is kind of like n equals 5, for example, right? So this might be n equals 1, for example, and n1 might correspond to 3 megahertz, or something, right? So here we've got it's a single frequency. We've got one peak. So in this case, we've got two frequencies. And so we get two peaks. We have two coefficients. Okay. Now, typically, this analysis is done in like FPGAs or high-speed processors, and they're extremely fast and they can do it really fast. But to do this kind of analysis in a computer, it takes a while. It takes a lot of computing power. So as an example, back in 2017, I built this RIDI PSK transceiver that I took down to FDIM, as a matter of fact. And this came out of a conversation I had with Paul Darlington a year or two before at FDIM. And we were talking about these modules he had. He had these sudden RX TX modules, which had a footprint for a Arduino to plug into them. And they were basically a 40-meter transceiver that you could control with a Arduino. And so I was talking to him, and he said, there's no way a 16 megahertz, 16-bit Arduino could decode RIDI and PSK. And I love a challenge. So I took it upon myself to go figure it out. So I took out of the RX modules, I sampled the audio coming out at 9600 hertz, 10-bit samples, and I used two tones, 830 and 1000 hertz. So I tweaked the passband so I'd get those frequency for mark in space. And I used correlation, not an FFT, to detect the 830 and 1000 hertz signals. Here you could see the blue is the 1000 hertz signal, 1 kilohertz. And the orange is the 830 hertz signal. So, and here's a demonstration of that. So what I actually did, I didn't use correlation, I used something called autocorrelation. Okay, so in this spreadsheet, this was what I used to design my algorithm. So let's take a S9 830 hertz signal, and let's do the correlation here. And so this is the output of the correlation. You see we get a nice peak here at about 11. And so that corresponds to 830 hertz. So if I run this in my microprocessor, in my little Arduino, I run this autocorrelation, and I found a peak here, which is really strong. You know, it's 400,000 counts. Then I know I've got a mark or a space. Now, if I go down to a really weak signal, S4, and I do the same thing with an S4. And if you see here, the count's about 300 counts. So here now the count's down around 8. So in reality, this would be buried in noise. You'd have a noise floor. So this is a theoretical exercise. You wouldn't be able to detect this, but the algorithm was able to detect the peak at 11. So in the same thing, we could do the same thing for, you know, an S4 1 kilohertz signal. And now the peak shifts over to about 9, right? So I knew that if I got a peak around 9, it's a 1 kilohertz signal. If I got a peak around 11, or no, 12 or so, whatever that was, I know that it's a 830 hertz signal. So that's kind of how correlation works. But this is called autocorrelation. What you're doing, you're correlating it with itself. Okay, so now this is we need to talk about continuous versus discrete, because remember back here I talked about, you know, this equation is based on an, you know, this here is based on an a function, which is a blackboard equation, right? And that blackboard equation is continuous, right? It's like this. It's a blackboard equation, okay? But what in the real world, we're seeing this. We're seeing discrete points. We're sampling the waveform at various points, and we're getting values. We're getting numbers coming in. This is a discrete. So we can't really use the continuous Fourier transform. We have to use a discrete version of the Fourier transform because we're seeing points. And your scope is actually doing a discrete, even though your scope is plotting a nice trace like that, it's actually a discrete, but it's sampling so fast, it's almost as if it's a smooth curve. So with a little bit of math, you arrive at these equations here. So in this example, let's assume we've got 46 values, and the values are x at n. So x0 is the first one, x1 is the second one, x2, x3 is the next one, and so forth, all the way up to xn, which is 46. In this case, the nth, the last one is 46, right? Or it's 0 to 45, right? So the only reason why I'm showing you this so that you understand what n is, because n is going to become important. So n is just the index of the value we're looking at here. Okay, makes sense? So for example, x0 is 0. x1 here will be 13, which will be this point. That's x1. x2 will be this number here, which will be 15, and so forth. Okay? So n is, in this case here, this summation, n is the total number of samples. In this case, it's 46. N will become important when we look at the Fourier transform in LT Spice, in a fast Fourier transform. N becomes very important that you understand what n is. But n is the total number of samples that you've captured. So keep that in your back of your mind. In this case, it's 46. Big N is 46. Little n is the index. Little n is the index, is telling us which of these values we're dealing with. So we're summing across all the values. So this little x at small n here is actually these values. And we're just doing some math and we're just summing it together. K now is another special number which you have to know, but you don't have to know it. K is called the bin number. Okay, and it's going to become important. But think of K, this large X, K, large capital X, small k, that becomes your coefficient to say, okay, how much of 1 megahertz? So X, for example, X1 might be 1 megahertz, X20 might be 13 megahertz. So XK is just telling you the strength of the frequency for the K bin. And we'll talk about that in a second. Oops, what did I jump ahead? Oops, I jumped ahead, way too far ahead here. Okay, so this is the discrete Fourier transform. It's got cosines and complex numbers and sines and all this stuff. And if you have to do this in a computer, it gets quite hairy. And enter in something called the fast Fourier transform. So the fast Fourier, so we talked about a continuous Fourier transform, which is on the blackboard, right? We talked about discrete Fourier transform, which is the points. And I gave you an example of like the correlation example that uses discrete points. In my case, I said I used 32 points. If you come back here, I said I used a buffer of 30 samples. So my N was 30, right? See, N was 30 here. And so now we're going to enter into the fast Fourier transform. So the fast Fourier transform is an optimized form of the discrete Fourier transform that's used in computers. And it's based on these things called butterflies, and they're just multiplications, and you can see it's in the shape of a butterfly. You've got like the wing here and another wing here, and you see it's all got little butterflies. They're called butterflies. We're not going to talk about butterflies, but that's just the way that the FFT works. It's you use this mechanism to generate your Fourier coefficients. Now, this is important. Some of the things I'm going to talk here, it's important because if you're going to do an FFT in LT Spice, you have to understand this. Okay, for an FFT to work, that's a fast Fourier transform. For the FFT to work, the samples must be an exponent of 2. Okay, so it's got to be 4, which is 2 squared, or 8, which is 2 cubed, or 16, which is 2 to the 4th, right? Or 2 to the 5, or 2 to the 6, or 2 to the 7th. It's 2 to the y, right? So the number of samples you're going to enter into the Fourier transform must be a exponent of 2. If it's not, the fast Fourier transform pukes. Okay? Your sample frequency that you're sampling at determines your resolution. Most of the time in LT Spice, we don't care about that. In your scope, that's taking care of it for you. You don't have to worry about it. In your spectrum analyzer, that's taking care of it for you. But if you're ever going to write your own program for FFT, this becomes important. The sampling frequency determines your resolution. And for example, let's assume we're sampling at 128 kilohertz. Then we could only resolve, the maximum frequency we can resolve is 64 kilohertz, and that because of this thing called Nyquist. You'll hear people say, oh, that's Nyquist. Well, Nyquist says we can only, the sample frequency, the maximum frequency we can resolve by sampling at a given frequency is half of that frequency. So 1/2 of 120 kilohertz is 64 kilohertz. That's the Nyquist frequency. So the bins, remember we talked about K, the bins? The bins are the frequency resolution. So in this case, for like n samples, the frequency resolution bin, in this case, is 64 kilohertz divided by 32. The Nyquist maximum frequency we resolve divided by the number of samples comes up with 2 kilohertz. So our bins, each K represents 2 kilohertz of bandwidth. So K1 would be 2 kilohertz. K2 will be 4 kilohertz. And so forth. As you go up, you're only able to resolve 2 kilohertz chunks. That's really important because you can't really resolve like 2.5 kilohertz, or in this case, you can't resolve 3 kilohertz because you're going up, you're jumping up in steps of 2 kilohertz. So the interesting to note here, and this becomes important with LT Spice, the more data points you have, the higher your resolution. So in this case, we have 32 samples. If we double that, and we went to 64 samples, then we would resolve to 1 kilohertz. We can resolve our resolution goes up. And if this was 1,000, then our bin size gets really small and we'll be able to resolve fractional hertz, right? So the maximum, another thing which is important, again, your scope and your spectrum analyzer does all this for you. You'll never see it. But if you're going to be writing your own FFT, this is important, is that the maximum frequency we detect is half of the bins. So even though we've got 32 samples and our K goes from 0 to 32, we can only resolve half of them because what happens, the FFT wraps around at n divided by 2. And I'll show you an example of that in a second. So we can only resolve half of the bins. The other half is just a mirror image of what we would see. So in this case, so bin 4, which is our X4, if we go back to, our fast Fourier transform, that's the coefficient. X4 is what the 4th bin is seeing. So this is what you would see on your spectrum analyzer or your scope. You would see a peak there. You'd see a peak at X8, at bin 8 or at bin 12 and so forth. Okay, so here's an example. I'll just show you this quickly so you understand what I'm saying about aliasing. Okay, so here's an example. So here's the spreadsheet, and I'm doing a fast Fourier transform, and I'm doing it in Excel. And if you get the data analysis add-on for Excel, you could do a fast Fourier transform in Excel. And all I'm doing here is I'm just calculating the sine based on these numbers here. So that's my frequency. That's the number of samples. So I got 64. That's my N. My sample frequency is 32. My sample rate, each bin is 0.5 hertz. So if I do an FFT, here's the FFT here, and here's the signal itself, and here's my FFT. Now, since I'm doing 64 at 32, it wraps around. So this portion is a mirror image of this. So if you count the number of dots here and you count the number of dots here, it's the same. So right here, this is a mirror image of that. And if you go here, you'll see that at bin 12, okay, we've got that value, which comes out, the magnitude is 32. And bin 12, since each bin is 0.5 megahertz, it comes out to 6 hertz or 6 megahertz or whatever you're measuring. And sure enough, that's what we're seeing here. Okay, if we've got 4, so here I've got 4 functions I've added together, and that's what it looks like. You know, I do my FFT, same thing, 32, it wraps around. Those 4 peaks are just a mirror image of that peak, of these 4 peaks, and you ignore anything after 32. You only look at the lower n by 2 numbers. And again, this is just theoretical. You don't have to worry about this in your scopes or your spectrum analyzer. This is all taken care of for you. But what's interesting, you can see now, as if in my signal, if I put a gap in here, now look at my signal. It gets wider. It's no longer 1 point. It's now 1, 2, 3 points. It gets wider, and I get a little bit of noise, a bit of junk at the edges here, right? And that's just because I have zeroed out, I've put in a bunch of values here. And this is where you'll see something called windowing. This is where an FFT, you would window. So you'd apply a window to get rid of this. So you'd say, okay, I apply a window on my signal, and I only want this section of my signal. And what it does, it gets rid of this nonsense. Same thing if you coming in with zeros at the start or end, same thing. Now ignore, again, after 32, ignore that. That's just a mirror image. Look at here. All of a sudden now, my peak is 1, 2, 3, 4, 5, 6, 7, 7 points. Huge. And that's because of the zero. And this is where you'd apply a window. You apply a window to get rid of these things at the start and end. Now, we're not going to be talking about windowing here, but window is more so for real time, where you want to just take a signal and you've got some junk in the signal. Okay, so now finally we get into talking about LT Spice. Okay, so how are we doing for time? 8:17. Okay, so the way you do a FFT and LT Spice, you generate a signal. So in this case, I use this little circuit here, and I generate a signal called V sine, and it's 1 volt peak at 1 kilohertz, right? Signal. And here's the plot here. So you right click on the display window. This window comes up, you hit view, and you go over to FFT. So you right click on the display, you click on view, this pops up and you select FFT. Then this window crops up. And this is where now N and your windowing and all this stuff comes into play. Okay, so the first thing you got to do, these are all the voltages. You select what voltage, what plot you want to see, what voltage or current. So in this case, we want to see V sine, which is this plot here. So we would select V sine. That's telling us the number of data points. Now, notice this data points is a exponent of 2. So even though it looks pretty large, it's 2 to the 18 is 262144. So that is in fact, that's a default it comes out to. Now the number of points here, that's just, it averages. So it takes 3 points, averages it. So in case you got some noise, it kind of smooths it out. And here's your windowing function. Remember in the plot, I showed if you got some gnarly stuff, you could window it to get rid of it. In reality, in LT Spice, I can't see you ever using a window function unless you've got some really wonky circuit. But it's more so windowing. I think it's more so for real-time data, but someone may know better than me. So let's look at example. So here, so when you do an FFT in LT Spice, this is what you get as a default. Okay, you get this big, huge peak. And remember, we saw in my plot that if you've got some zeros or you got some bad data, you got this big, wide peak. So all of a sudden, you've got this wide peak across 1 kilohertz. It's a 1 kilohertz signal. And then you got all this crap coming out. This should be a pure sine wave. It should only have 1 point, right? 1 kilohertz. And if you look, this crap is pretty strong. Now, yes, 60 dB, minus 60 or 70 dB down is low. It's not a lot. That's pretty low down, but still, for a pure sine wave, that seems a lot. Look at all this crap. So it's like, you know, we've got the cat becomes angry, and it's like, what's going on here? So this is resolution number 1. This is how you fix that. It comes to n, the value of n, right? How many sample points? Even though it's taking 262, 144, I don't think it's generating that points, right? So what we need to do is we need to get it to generate more points. So in the case of the FFT I did here, I used 10 milliseconds. Now, if I don't do anything, all I do is I increase that to 100 milliseconds. I run the same FFT. All of a sudden, it starts looking better. My point becomes sharper. Look at that. It's no longer this wide peak. It becomes sharper, but I still got a lot of junk. And the other thing, this is going out to like what? 10 megahertz. This is a 1 kilohertz signal. Do we really need to go out to 1 megahertz or 10 megahertz? That seems a little bit excessive. So we need to fix that. So the first thing you need to, for your FFT and LT Spice, you got to make sure you're generating a lot of points, a lot of data. So now comes this number of points. So even this is not telling you how many points, how much data points it's generating. It's telling it how much data points to use. So the FFT is using all the data points from 100 milliseconds. It's using all those data points, but we're saying for our calculation, okay, use, what was it, 2600, whatever, right? Now, because it's using that many data points, it's taking it out to 10 megahertz. If we were to reduce that to say 4096, okay, all of a sudden now we go to say, what's that, 10 kilohertz. We're going out to 10 kilohertz, right? So we're getting a better FFT. Still a little bit of noise here, still a little bit of junk, but notice it's dropped down now, 110 dB down. So fix number 1 is to increase the number of points, make this slower time that you're going to go. So in this case, 100 milliseconds. And the time step, if you go to 50 nanoseconds, it generates even more data points. So you get this nice chart here. And if you go to 4096 here, you reduce the maximum frequency you're going to see. Okay, so the next thing, to clean this stuff up now, to clean this junk up now, in LT Spice, there are some defaults that get set. And these defaults causes us grief. And the first one is this plot win size, which is telling it to compress. So in the background, this is a default setting. It's saying to compress 300 data points. Okay, and when it's doing that, you're losing resolution. So one of the things you have to do is disable this compression by setting plot win size to 0. The next thing is that the default for the number of digits, number of decimal points, right? Number of digits it's going to use is 6, which is a single precision floating point. We want double precision, so we want to increase the number of digits. And it says here, if it's greater than 6, it becomes double precision. So I used 8. And so if I add those two SPICE directives, I run my transient analysis, 100 megahertz, 50 nanosecond timestamps, and I do my FFT. Look at this, sweet. Flat, no garbage, one nice peak, which is what I would expect. We have a happy cat. Okay, so now you guys are going to hate me because I talked about all this Fourier stuff and correlation and all this stuff. And in LT Spice, there's a fast and easy way of doing this. And you guys are going to probably, next time you see me, you're going to drop kick me and go, why did you go through all this crap with me? Because it builds character. So in LT Spice, there's a Spice directive called .4, .Fourier. So the way it works is you enter a SPICE directive called .4, the frequency of interest you want, say 1 megahertz. In this case, the case we've been looking at is 1 kilohertz, right? The number of harmonics we want to analyze. So it could be 1 harmonic, 5, 10, 100. How many harmonics you want to analyze? And the number, this is the number of periods, the number of data. So number of cycles, so the number of data. I usually use -1, which means all. If you use -1 here, it means all. Okay, and I think if you leave it blank, it also means all too. And then the data trace is the actual, the trace that you want to show. So in our case, it was V sine. The voltage of V sine, right? So if you enter this SPICE directive here, right up here, you enter it there and you run it, you'd end up with something that looks like this. It gives you the DC component, which is that, remember that A0 term, right? It tells you if it's got a DC component. And then it tells you the frequencies. So here's a harmonics. In this case, I said 1000 hertz, 4 harmonics, all data points, and look at V sine. Okay, so there's my 4 harmonics, which is 1 kilohertz, 2 kilohertz, 3 kilohertz, 4 kilohertz. And then it's telling me the strength of the 1 kilohertz signal, 2 kilohertz, 3 kilohertz, 4 kilohertz. So these will be like your peaks. That'll be giving you the peaks in your FFT plot. Then this here is really cool. It's giving you the normalized component. So it's taking the fundamental and it's dividing all the values by the fundamental. So the cool thing here is because it's done this, you could get now the dB, how far down it's in dB. So in this case, if you take this number, 4.99 times 10 to the minus 7, you take the log of that, again, log 10, not log E. You take the log base 10 of that, right? And you multiply it by 20 because we're dealing with voltages here, not power. You would get how far it's this signal down from the fundamental, which is pretty cool. Now, the cool other thing here, it's telling us the total harmonic distortion. So what is that? So the total harmonic distortion, it's telling us, it's giving us a measure of how much harmonics we've got. So it's mainly used in audio to tell us how much harmonic distortion we have in audio. Now, the way it works out is you've got this equation here, and it's the root mean square value, square root of the sum of the squares, square root mean sum, right? So basically what it means, if you take this, This is your Fourier spectrum. This is your, from your spectrum analyzer or from LT Spice or from your scope or whatever. You've got the fundamental, okay, and your fundamental's got strength, that's the magnitude. Here's the next harmonic, here's the next harmonic, so forth. So if you take the square root of the strengths of all these harmonics, you sum them and you divide by this harmonic, the strength of this, the fundamental, right? That gives you the total harmonic distortion. So that's an important parameter for me when I'm measuring my amplifiers, because I don't have to go through and do these stupid FFTs and be measuring the peaks. I could just use this .4 command. And so, remember we said that, it's, this in Canada, we need to be, for 10 watts, we need to be 44 dB down from the fundamental. I'm just using DBC, right? DBC's carrier again, but it's fundamental. So we assume 44. So if you look at, with a little bit of math, you solve this, you'll find the strongest harmonic has to be 0.63% of the fundamental. So let's do a little experiment here. Let's have an LT Spice circuit. We've got our fundamental, which is 1 kilohertz, magnitude 1, strength 1 volt. And here we've got a second signal, which is 3 kilohertz, which is the, what's that? Third harmonic. It's the third harmonic, right? And we set the voltage of that to 6.3 millivolts or 0.0063 volts, right? 6.3 millivolts comes out to 0.0063, right? So if we do that and we plot it, this is what we get. And a little bit of math here, 20 log 0.0063 divided by 1 is just basically 20 divided by 6.3 millivolts, which comes out minus 44, which is what we wanted here. So, the math works out. So if we were to use the .4 Spice directive in LT Spice for that little circuit we've got here, right? We add the .4. And as I said, where I had it, .4, 1004 minus 1, we add that directive there. Okay, and this is what we would arrive at. Our fundamental, that's the strength of it, the second harmonic, the third harmonic, and so forth. And if you look at the strength of it, look at the third harmonic. It comes out exactly 6.3 times 10 to the minus 3. So if we take log of that times by 20, it comes out to 44, right? And look at this. Look at the total harmonic distortion. It's coming out to 0.062%, 0.063%, which is what we need. So I could use this now, and I can figure out whether I could figure out the spectral purity. I don't need to go and do all that rigmarole with LT Spice. So last slide. So let me put this in a nutshell for you. Okay, so use the Fourier transform to decompose a continuous signal. That's the blackboard, right? You use the discrete Fourier transform to decompose a sample waveform to get the frequency components, and that's what your spectrum analyzer does, right? And use the fast Fourier transform to optimize the discrete Fourier transform to do it faster and with less math. So typically you may get that in your scope, although your scope may have an FPGA in it, I don't know. But certainly a microcontroller is going to be doing an FFT, and in LT Spice it's doing a FFT. There's some rules when you're using an FFT. Key one is it's got to be an exponent of 2. If you go into LT Spice and where was a little signal here, and you went in here and you put in a number other than a power of 2, your LT Spice would puke. LT Spice would puke and would come back with an error. Okay, your sample frequency is important, bin size, all that stuff, right? By default, LT Spice does a crappy job of doing an FFT. You got to disable compression. You got to change the decimal precision. You got to increase the number of data points, i.e. longer simulation time and faster computation interval. And you reduce the number of data points in the FFT to match the total bandwidth. You're not reducing the number of data points to use in your calculation, using the number of data points, the number of bins, right, to reduce the overall bandwidth. Okay, and it's far easier to use the .4 directive, which gives you the strength of your harmonics, provides you the DC level, and the nice thing, it provides you the total harmonic distortion, which is really important. So at that point, I'll end this, and the next presentation we'll talk about doing measurements in LT Spice. And let me see, how do I stop this? There we go. So there, any brains broken?
You lost me at, you probably won't understand this. How much time do you think you devoted to learning all that stuff?
All that stuff? Years.
Okay.
Literally years. And the nice thing about doing this presentation and figuring out, like going in and actually understanding what I'm looking at, okay, that's helped me a lot. Because when I need to, the way I learn is by explaining it to someone else. And if I can explain it to someone else, I learn. That's why I choose difficult topics. I don't choose easy topics to present about. But the good news is, and this is the takeaway from this, all that stuff I talked about, it's all done for you in your scope or your spectrum analyzer. You don't got to worry about it. If you're a programmer, yes, you got to worry about it. If you're using LT Spice, some of it becomes important. That's the takeaway.
It's all those LT Spice, it's all those options you had put in.
Right, and that's all. That's if you just use the .4 command, a lot of that nonsense goes away.
Okay. Yeah, this brought back memories of college in 78 to 80.
Yeah, so I think Hassan put his hand up.
Yes, could you hear me?
Yep.
All right. Well, it's a nice presentation and it's spot on the theory, but I thought of a way to explain it in 2 minutes if you want to hear it.
Sure, go ahead.
Okay.
Yeah, make me look silly.
No, I'll try to be as silly as I can.
Yeah, throwing them under the bus.
Yeah. Okay, so imagine we're at field day on FDEPI, field day on Eric's private island. So Dave, Peter, and Eric are there on the island. They're all on different parts of the island. So the bands are empty and they all have transmitters. So they're transmitting CW. So let's say Dave is transmitting CW on one band. Eric's listening. So you see this continuous tone coming in, right? Let's assume it's just a continuous tone. It's like just that. So if Eric wants to, normally you use your ears to listen, but let's say you want your computer to figure this out. What you do is Eric's got a function generator. He knows, he just sweeps the frequency until, and then he takes the antenna signal, has a function generator, just plays with the frequency dial, mixes the two. You have a mixer. You pipe the output of the mixer, low pass filter it, and put a DC voltmeter on it. What you should see is the frequency is 0. And this is because of all the stuff you talked about. If you have, actually, let's get to this first. At one point, he finds one frequency when he's at the same frequency Dave is at, and he's at the same phase. he should find the DC value jumps, and there's like it peaks. It's a max. That only happens when his local oscillator is at the same frequency as the Dave and same phase. And if now let's say Peter jumps in and starts transmitting on a different frequency, it's not going to change the result, because the thing is, it's just, that's the beauty of the Fourier transform. You, when you do this, the correlation operation is equivalent to mixing it and measuring the DC value, so one scalar value. Any other frequency, you add to it, doesn't change the result. So that's the point of the Fourier transform. That's the whole magic of it. So all the other bands are not, will not be picked up by this mixer thing. At the same time, now let's say Eric wants to figure out who else is on the island. He just sweeps the frequency band and then just writes down all the numbers for each frequency point. And now he's got a Fourier plot, Fourier transform magnitude plot.
Right.
And
so your mixers basically.
I did some hand wavy thing about the
recording is on.
I did this hand wavy thing about the phase thing. So you can do Fourier transform two ways. You can either basically, you sweep the frequency and you adjust the phase. You can do it that way, so you have like a frequency plot and a phase plot. Or you do it the simple way. You just have one sine wave. Like you get a sine wave. Your local oscillator has a sine wave at one frequency. Flip a switch, it generates a cosine wave at one frequency. Now you have two numbers. Treat them as a complex number, and you can get the phase and frequency from there.
Right. So basically, remember that discrete Fourier transform, you're showing a sum, or even the continuous. Well, it's showing an integral, which is a sum. So basically, that's what you're doing. You're just summing over all the frequencies. When you tune the band, you're summing it over all those frequencies.
Yeah. If you want to know the magic of the Fourier transform, why it works, all you have to do is draw a sine wave and draw an identical sine wave, multiply the two, and then see how much overlap they have. And so it should be like 100%. Now you draw a sine wave of a different frequency, and you should see the overlap between the two is a lot less, and half the time it's positive,
Right.
half the time it's negative, should average out to zero. If
Right.
it doesn't,
That's the correlation.
right. So if it doesn't average out, you just keep going over a larger number of cycles, like 10,000 cycles of the wave out to zero. That's why you need a really long duration Fourier transform, like a 1,000-point FFT, they call it. You need a lot of cycles before it really averages out to zero.
Yeah, and that's why I was saying that number n is very, very important. It tells you, how much you're going to resolve. The more data points you have, the more narrow the frequency resolution. The fewer data points, the wider the frequency resolution you're going to get, right?
Yeah, so if you want to build an analog function for FFT or Fourier transform circuit, just get 1,000 function generators, all tuned to a slightly different frequency, regularly spaced. Just have 1,000 mixers, mix each of those function generators with your input signal, measure the DC output with 1,000 voltmeters, and plot them on a piece of graph paper. Frequency on the x-axis, voltmeter output on the y-axis, and you will see only the function generator, only the frequencies for which there is an active signal coming in will you see a positive value, and you'll have a whole plot of your spectrum for over the range that you've tuned your frequency generators for.
That's actually a really good analog equivalent, right?
Yes, the brute force method.
Yeah.
And expensive.
Yes.
Well, it's what did Einstein used to call these things? Jagotkins. I think I pronounced it right. It's a thought experiment, right? The song's not saying go out and do it. It's a thought experiment, right?
Right. Gedanken
experiment. What's it called?
Gedanken experiments.
Godonkin, okay.
Yep.
Go ahead, Peter.
That was more like 4 minutes or more, not 2 minutes or less.
Sorry.
On the other hand, it was interesting. And actually, some of the things you were saying, Dave, you recall we were sitting with Farhan a few years ago, and he went up and got his spectrum analyzer that he'd built. And the way some of Hassan's analogy reminded me of that project. So I have a question that was pre your .4 statement. When you were doing all the adjustments to clear up the FFT on LT Spice, could you not be hiding something of importance?
No, it's all junk. Because what happens in LT Spice, zoom in on your signal. Take that sine wave that looks nice and smooth and keep zooming in. You know how to zoom in, right? You right click and you draw a box.
Yeah.
You right click on the signal, you draw a box around the signal, and you zoom in and keep zooming in and just keep zooming in. And what you'll see is points, straight line, point, straight line, point, straight line. And all those straight lines are introducing noise. Right?
Okay.
So by you generating more points, those straight lines become closer together. And it almost becomes a continuous function. So all those little interpolations between the points, that's what's generating all that shit.
Yeah.
Okay. Yeah, thanks for this, Dave. I know it was a lot of work, and a lot of it don't understand, but bits and pieces I do, and that's what makes it interesting and fun. So thanks for that. And I started off with water. I've now switched to beer, and before this is over, I will be into the whiskey. Thank you very much.
Take some time
And
out too.
I think Dwayne has got his hand up.
Go ahead, Dwayne.
Yeah, at the company I worked for about 30 years, they had a division that basically all they did was FFTs and basically Fourier Transform infrared spectroscopy. And it was amazing watching what these people who made a living doing FFTs did. Back when I started in the early 80s, well, they built their own processor because there wasn't anything around fast enough for it. And they did a 20-bit processor so they could run single precision math and get just about the same values as people doing double precision. But they had FFT array processors. It did 4,096 point FFTs in about 2 seconds, and you could put two of them in the box, and they would interleave to do FFTs on infrared signals from whatever sample you were looking at. They ended up building up databases of almost everything. You could go and do an FFT on a paint chip from a car, and they could tell you what model paint it was used in that. When you get to something that we can do, there's some fairly decent things on an Arduino for doing FFTs. We've got a integer version of an FFT that will get you up to about a little over 4 kilohertz maximum frequency on a input signal, just using the straight nano. If you're interested in playing with FFTs and actually looking at higher frequency audio stuff, there's a program out there called Visual Analyzer. It's freeware, shareware, or whatever you want to call it, that basically does FFTs using an audio sound card, and it basically gives you a response to about, depending on sound card, to about 20 kilohertz. It has the things in there for computing total harmonic distortion and all kinds of other fun things to play with.
Yeah, and I'm sure Dwayne, I'm sure there's a ton of tips and tricks and little things people have done over the years to optimize this, because it's such a fundamental thing. I remember I saw one implementation of it was a DSP library, and as part of it, they had a FFT call. And believe it or not, they had a sign table, a lookup table. and it would go and it would look up values, right? And it would actually look up the value and interpolate between the values. If you're looking for a number between a assigned value between these two numbers, they would interpolate it. And I saw that, I think it was in the PIC world, as a matter of fact, where they had these lookup tables, you know, just to get the speed, you know. So yeah, I could see that, Dwayne. There's a ton of ways to optimize this stuff.
One of the projects I made a couple of years ago was a little simulated analog voltmeter. It used a Arduino Pro Mini and a little LCD, little OLED display. And one of the functions I had in there was a spectrum analyzer that basically gave me a display up to about 4 kilohertz with 128 points on it, and it's amazing what you can do with something like that.
Yeah, and that's what, and you know, that was my comment that started that whole RIDI PSK conversation with Paul Darlington, is that, you know, there's a lot of processing power in Arduino, like a 16 megahertz microprocessor. See, Mike, there's a ton of processing available that you could do all kinds of cool things with it. You just have to be clever. That's all. You just can't go in and expect it to do the same level of code that a PC would do. You just got to optimize it. And I remember way back when, Dwayne, I remember one of the first things we were talking about was that it was it the 9850. That was the analog, the chip that Wes Hayward used to do power meters. What was that chip?
8307. Yeah.
8307.
8307. I remember, Dwayne, you were saying, hey, look, there's a way you don't got to. It's a very simple multiplication, and it was a really clever way to arrive at a value without using a whole bunch of floating point. And that's what I'm saying. You just got to get clever in terms of how you use these microcontrollers.
I think I posted a link to an article on somebody's making a little transceiver for the digital mode that's similar to what the QDX does. I ended up ordering some of the boards that'll be coming in a month because I was too cheap to pay for fast shipping. But basically what they're doing is like zero crossing detector to actually go and just measure the time between cycles to actually get the frequency on the incoming signal that they're using, and then transposing that up to the HF frequency. And as far as receiving code, you know, RTTY and stuff like that, you bring it down to baseband, and you've got all in the world to play with 16 megahertz.
Yep, and I think I did something similar for the PSK because I was looking for zero crossing, right, in my correlation.
Okay, cool. Anybody else? Comments, questions? No. Very good, Dave. You lost, like I said, you lost me when you said our head's gonna hurt. It was very good, though. Thank you.
Yeah, I found it very interesting. Not that I understood it, a lot of it, but it was good. Thanks, Dave.
Okay, so go ahead, Pete.
Yeah, one comment, Dave. On a few simulations I've done over the years, and then I've seen this plot win size equals 0 stuff, and I can never figure out exactly what that was. But now you showed me. I won't say it kept me up at night. You're still muted.
Yeah, the name of it makes no sense whatsoever. Plot win size, like, come on, you know, like it's a compression. That's what it is.
Yeah.
Okay.
Yeah, the guys at Linear Technology, it's a, you know what, it's the more I dig into it, the more features I find. Like I didn't know anything about the .4 command. I was planning to go and measure these amplifiers and look at a spectrum and measure the purity and then do the same thing. And the .4 command simplified it so I could do it in like seconds.
Yeah, but do you find that LT Spice is very close to Spectrum Analyzer?
Yeah, but you see, remember I said at the start, I'm not measuring this. This is all my entire series of talks. It's all about LT Spice. Because the minute you have to go and start measuring stuff, that's when a month-long presentation takes 2 years. I'm exaggerating, but you know what I mean. Because now all of a sudden you got to bring the real world into your measurements. LT Spice is great because it's all theoretical.
Yeah.
You plot it, it's all on one screen. You can do it on a computer screen. You don't have to go start soldering parts, and you've got a bridge, or you got your trace isn't right, or you got RF bleeding through.
Anybody else? I guess that's it. So does anybody want to bring up anything new or discuss anything? Oh, I guess that's it then. Well, shall we call it an evening? Alrighty. All right, gentlemen. Go ahead, Michael.
I thought we had talked about discussing what to do with the ongoing YouTube, the ongoing recordings for later on. I presume we're going to keep uploading from now on to YouTube. Wasn't there an agenda item to talk about that?
Yeah, right. Because that's correct, Michael. Because look at all the work it took us to get those recordings up. So as we record stuff now, how are we going to get that put into a format that we could upload to YouTube? So that's going to be the key thing. Like, what's the process we're going to use? We have a process, but it's now a matter of who's going to do it on an ongoing basis, right?
You could assign. You could ask somebody to do it at each meeting. Perhaps one person to do each meeting, so not everybody has, so that no one person does them all. Maybe it's better to have one person do them all. I don't know.
Well, it's one recording a month, isn't it?
Yeah. Well, it's two.
Yeah.
It's two. It's processing.
Well, I volunteered to do the YouTube part of this, so I will maintain the YouTube channel, upload the videos, maintain the description. I've got the password now, and I can log into the YouTube channel, and it's a pain in the ass to go do it because it's MFA, it's multi-factor. You got to use a phone. So anyone who logs in, even though you know the password, your phone has to be entered in as a device, right?
Yeah.
So it becomes a royal pain in the ass. But at least we know the process. If someone wants to share, YouTube, maintaining, that's fine. I don't have a problem. But I volunteered to. I will upload the videos to YouTube, create the playlists, all that kind of stuff.
So if we have the videos made available like they are now, then I don't mind processing them to the way we're doing now. And then you can take them, Dave, as you do, and move them up to YouTube. If somebody else wants to join in on the fun, then if there's enough volunteers, then maybe we can divide. I can put a list together, a schedule together where somebody does it in July, the 2 meetings in July, and somebody else does it in August, September, that kind of thing. If there's enough volunteers, we can do it. We can go that route. But to get it going, I'll start off.
Yeah, you can put me down too.
Yeah, me
Actually,
too.
you know what? We should turn off recording, shouldn't we?
Yeah, good idea.
Let me stop recording.